Successive ionization energies. Remember that ionization energy is the energy required to remove an electron from a gaseous atom or ion. So let's look at a table that's going to help us to explain the trends for ionization energy. First of all, along the top of this table, we're listing the first ionization energy, followed by the second ionization energy, and the third, fourth, fifth, sixth, seventh, eighth. Okay, so those are our successive ionization energies. Going along the side of our table, we're looking at elements going from the left to the right across the third period on the periodic table. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. So first, let's look at how ionization energy changes as we go from left to right across a period. So we're looking at our first ionization energy, or our first column of numbers. And we're going to notice that the ionization energy gets bigger and bigger as we go from left to right. And again, the reason for that is as we go from left to right across a periodic table, we're adding more and more protons to the nucleus, so the nucleus becomes more positively charged. But we're adding the electrons to the same energy level, so there's about the same shielding as we go from left to right across the table. So the effective charge on the nucleus goes up as we go from left to right, so the hold on electrons increases, so the energy required to lose an electron gets bigger and bigger as we go across a period on the periodic table. Now let's look at successive ionization energies for an atom. And first, let's look at sodium. To remove the first electron, our first ionization energy is 495. Our second ionization energy, or the energy required to remove a second electron from the sodium ion, is 4,560. Notice that that number increases. When we look at magnesium, the ionization energy to lose the first electron is 735. To lose the second electron is 1445, and to lose the third electron, it jumps way up to 7730. Now let's look at aluminum. The energy to remove the first electron is 580. The second electron is 1815. The third electron is 2740. And the fourth electron is 11,600. What we should notice is that our ionization energy is increasing as we go through successive ionization energies. And that makes sense because we're removing an electron from a neutral atom with our first ionization energy, but we're removing an electron from a positively charged ion for each successive ionization energy. And if we try and remove an electron from a positively charged ion, it's going to be harder to do because there's a greater attraction between the electrons and that positively charged ion. Now the other thing we should notice is the big jump that occurs when we go from removing valence electrons to removing core electrons. Like if we were to look at magnesium, magnesium has 2 valence electrons. So we remove the first electron, we remove the second electron, but when we remove the third electron, there's a huge jump in ionization energy because we're going from our valence electrons to our core electrons. Or if we were to look at aluminum, we remove the first, second, and third valence electrons, but when we get to the fourth ionization energy, we're removing a core electron, and notice that big jump in ionization energy. If we look at silicon, silicon has 4 valence electrons, so it goes up a little bit, up a little bit, up a little bit, and then when we get to the 5th ionization energy, we've got a huge jump because we go from valence electrons to core electrons. So to summarize this all up, in general, as we go across a period, ionization energy increases because the effective charge goes up. Adding electrons in the same principal quantum level or the same energy level do not completely shield the increasing nuclear charge caused by adding protons. And also we should notice that the first ionization energy is considerably smaller than our second ionization energy. And our reason for that is the first electron is removed from a neutral atom And all successive ionization energies are removing electrons from positively charged ions. The increase in positive charge binds the electrons more firmly, and the ionization energy goes up. Note the large jump in energy when we go from removing valence electrons to removing core electrons. Now we want to get into the formation of binary ionic compounds. So let's just break that word apart first. We know that binary means two. Ionic means we're looking at ions, positively and negatively charged particles that have either gained or lost electrons. And the word compound just means that we're joining different particles together to function as a unit. So binary ionic compounds are solids that are formed between a metal and a nonmetal, or something on the left side of the periodic table combined with something on the right side of the periodic table, or something that has a low electronegativity and something that has a very high electronegativity. That causes a transfer of electrons. And since we have a transfer of electrons, we end up with charged ions. And the oppositely charged ions together have a lower energy than they had when they were apart. And we know that matter tends to go towards lower energy. So this energy is referred to as lattice energy. The energy released when an ionic solid is formed. So if we look at an example, we've got a gaseous positively charged ion and a gaseous negatively charged ion. And when those ions are attracted to each other and come together to form a binary ionic compound, they're at a lower energy state. So the sign on that process, or our lattice energy, will be an exothermic process, so it will always be a negative sign. So let's look at the formation of ionic solids from their elements, and we want to keep in mind that this type of change is a state function. So here's an example. Let's say we start out with lithium solid and gaseous fluorine, and we want to deal with the energy associated with taking those two elements and combining them together to make the binary ionic solid lithium fluoride. Well, a couple things have to happen before we can actually make that binary ionic compound. First, both of our substances have to be gases. Sometimes they are, sometimes they're not. Second, they have to be in their ionic form so that they're attracted to each other to form that ionic compound. So we've got a series of steps that are going to take place. If we notice that this particular example, lithium is a solid. So our first step is going to have to be to change it to a gas. And we should remember that when a solid changes directly to a gas, we're looking at sublimation. And that's an endothermic process. We have to add energy in order to go from a solid to a gas. And we can quantify that value. For lithium, 161 kilojoules of energy have to be added in per mole of lithium solid that turns to a gas. Then we need to change those lithium atoms to lithium ions. So we're looking at ionization energy. And again, we know that to remove an electron, we're going to have to add energy in. So our first ionization energy for gaseous lithium is 520 kilojoules per mole. Now our lithium ions in the gaseous state are ready to combine together to form our binary ionic solid. Now we're going to look at fluorine. It's already a gas, so we don't need to do that part, but we do have to get to atoms, and right now we're at diatomic molecules. So our first step is going to have to be to change fluorine as a diatomic molecule into atoms of fluorine. So we're going to have to break some bonds. We know that breaking bonds is a endothermic process, and we're told that the value for the breaking of those bonds is 154 kilojoules per mole of fluorine in the diatomic state. But we don't have a mole, we only have a half a mole of diatomic fluorine. So we're going to have to take that 154 and divide it by 2. And that'll leave us with 77 kilojoules per mole required to take that diatomic molecule down into atoms. Now we have to take those atoms of gaseous fluorine and convert them to ions. So we've got gaseous fluorine atoms taking in an electron to perform gaseous fluoride ions. And now we're dealing with electron affinity. Since a fluoride ion is much more stable than a fluorine atom, we're going to be looking at a process that is an exothermic process. So our electron affinity, we're told, is negative 328 kilojoules per mole of fluorine atoms that become fluoride ions. So now we've got lithium ions and we've got fluoride ions, both in the gaseous state. We're ready to form our binary ionic compound. So our last state is going to be to take those ions and combine them together to form our solid binary ionic compound, and we're looking at our lattice energy now. And since lithium fluoride is much more stable than the lithium and the fluoride ions that it began with, we're looking at an exothermic process. And we're told that the lattice energy is negative 1047 kilojoules per mole. Now, if we want to find out the overall energy associated with the formation of lithium fluoride from its elements, we would add all of those processes together to give us our overall energy for our reaction. So we've got 161 plus 520 plus 77 minus 328 minus 1047, and we get negative 617 kilojoules for every mole of lithium fluoride that's formed from its elements. It's a negative sign, which tells us that we're looking at a favorable process. Energy is released during that process. Now let's look at an energy diagram for this particular example. And the energy diagram is going to summarize the process. We want to notice that most of the processes are endothermic and not really favored. So we want to talk about why this process will actually occur. So if we start over on our left-hand side, towards the middle, we start out with lithium solid and gaseous fluorine. And our first step is going to be to form lithium in a solid state into gaseous state, and then gaseous state into ions. All of those are endothermic processes and they're not favored. Then we're going to break the bonds between our diatomic molecule of fluorine and form fluorine ion atoms, which is again not favored. So why would this process take place when the first three steps are not favored thermodynamically? Because of what happens next. When gaseous fluorine atoms become gaseous fluoride ions, some energy is released, and that's favored. And when those gaseous ions combine together to form that solid ionic compound, we're looking at a major exothermic process. The overall energy for this process is negative 617 kilojoules. The reason why this process takes place is because lattice energy is such a large negative value.